Section 2.1 is the section on the addition property of equality. What we're going to do in Chapter 2 that's different from Chapter 1 is we're going to be working with equations instead of expressions. What makes an equation different from an expression is that an equation has an equal sign in it. The equals sign indicates what our words say, is that two quantities are equal to each other or they're worth the same amount. So for example, if I have 2 dimes, that's equal in amount to having 4 nickels. The equal sign means they're worth the same amount of money, even though they might look different. Our goal in Chapter 2 is going to be to solve equations. Of course, there's nothing to solve here, but we're going to be looking for solutions to equations. So if I have a short and sweet equation like x plus 2 equals 5, if I want to talk about the solution to that equation, the solution is the number that I can replace x with that will make the statement true. Most of us should be able to solve this equation by what we call inspection, which means by just looking at it and we can see what the answer is. But 3 is the number I can plug in for x that would make that statement true. So 3 is the solution to that equation. All of the equations that we're going to be working with in Chapter 2 are what are called linear equations. And linear equations mean that there's only x to the first power. We're not going to look at any x squareds or x cubeds, no 1 over x's in our equations that we see in this chapter. The nice thing about linear equations is that a linear equation is degree 1, like I said, which means x to the first. And linear equations have only one solution. So when we replace the x with 3 in the situation above, 3 is the only solution to that. It's the only number I can plug in for x that would make that statement true. When we're talking about the addition property of equality, everything we're going to do in section 2.1 involves adding and subtracting. So let's go back to our 4 dimes, and oh, we only had 2 dimes. Our 2 dimes and our 4 nickels. 20 cents on the left, 20 cents on the right. Now the addition property of equality says that as long as I don't throw that equation out of balance, I can really do almost anything that I want to an equation. And specifically with addition, if I wanted to come up and put 2 quarters on one side, that says 2 quarters, then this equal sign is no longer true. Now I have 70 cents on one side and I have 20 cents on the other. But if I put those 2 more quarters on the other side, then now this equation is still true. 50 cents added to the 20 that I had, 70 cents on the left, and I have 70 cents on the right, and that equation is still a true statement. If somebody wants to come up and borrow 10 cents from one hand, they can do that as long as they borrow 10 cents from the other hand. And if I take away 10 cents from each hand, then I still have a true statement. That equality still holds true. So when we're trying to solve an equation and find that solution we have for our linear equation, we're going to use these properties of equality to try to figure out what value of x makes our statement true. That means if I start with the statement x plus 7 equals 12, even if you can look at this equation and see what the answer is, I need you to show your steps. There's only one step here on your homework for full credit, because the problems will get longer and harder and we need to practice writing down our thoughts and communicating our steps to each other. If I have that 7 attached to the x with a plus sign, The inverse operation, or the opposite of addition, is going to be subtraction. I can add a -7, or we can think about subtracting 7 to get back to 0. Okay, so all I have on the left side of that equation is an x. But I know I can't do that, just randomly add or subtract something in an equation, unless I keep that equation balanced. Meaning whatever I take away from one side, I have to take away the same amount from the other side. Like when we took the 10 cents away from both hands on the last page. So I get rid of a +7 with a -7, and x plus 7 minus 7 leaves behind just a plain old x on the left side. On the right side, 12 minus 7 leaves behind a 5. Now the nice thing about, we can check our work. By plugging in the solution we got, the 5, plug it into the original equation and make sure that the statement is true. 5 plus 7 is 12. We know that 5 is actually the solution to that equation. Now similarly, if we started with a number and we know that we take away 3 and the result is -8, and I'm trying to figure out what x is, I can undo a -3 by adding a +3. I can get rid of a -3 with a +3. Now again, I can't just do that to one side, that'll throw off the equal sign. So if I add the 3 to one side, I have to add it to both sides. On the left, -3 plus 3 is 0. There's our additive identity. And we're left with x is equal to -8 plus 3, which is -5. Now the one thing to keep in mind is our properties of equality are true regardless of which side our x is written on. So maybe I have 9 equals x minus 2. I'm still trying to get that x all by itself on one side of the equal sign, and so I get rid of a -2 by adding that 2 to both sides. 9 plus 2 is 11. -2 plus 2 is 0, so all that remains on the right side of that equation is an x. Now in your book, all I'm going to assign are the problems that end up with a 1x on one side for right now. Your author gives some more, if you work a little bit farther from what I assign, that have some extra steps to them, but we're not going to start there until we're working together as a class. Now do understand that you might have to add fractions or decimals to both sides. X minus 1/2 equals 2. I'm going to have to add a 1/2 to both sides, and then I'm going to let you do the arithmetic from there. Or if I have x plus 6.9 equals -2.3, to get rid of plus 6.9, we have to subtract 6.9. And again, I'm going to let you do the arithmetic and put those together from there. So at the end of section 2.1, I would like you to do the following problems. Do 9 to 30, counting by threes, and then if you flip the page, see what you can get done with 74, 76, and 78.